In the last episode, we made a module which has 6 square wave oscillators that are voltage controllable and hard gateable. They are pretty good for generating some glitchy textures and so on and so forth, but are not enough for our system for sure. Moreover, the ICs we used in them are CMOS logic ICs, which are generally considered as digital. And today we're gonna do something very analog, which means that it won't generate just zeros and ones, like our square wave oscillators do, but instead will give us desired smooth curves and slopes. The idea of this module came to me when I was looking at Paya function generator, but the Paya function generator only behaves like an attack-release envelope. I enhanced it and made it not with field effect transistor and bipolar junction transistors, but with a logic integral circuit and an operational amplifier. Also, on the module we're making today, we're gonna have a free-to-use comparator and a voltage-controllable slew limiter, which can act as a filter. So let's jump right in and first learn how this whole thing works, and afterwards we're gonna assemble it and hear how this sounds. One simple thing you can make with an op-amp is non-inverting amplifier. The circuit is provided right here. I'm not going to explain how op-amps work because this is kind of a long topic. You can search up some articles. The wiki article about op-amp appliances is pretty much enough to understand that, but you can dig even deeper and find something for yourself. I'm going to give you the building blocks of what we're going to do today. So this is a non-inverting amplifier, which means it has an input and an output, and the voltage at the output is proportional to the voltage at the input multiplied by this cute little bracket. This coefficient is determined by these two resistors. If they are equal, say this is 10 kilo ohms and this is 10 kilo ohms too, we get 1 plus 10 divided by 10, 1 plus 1, get 2. So we get an amplifier in which you can put 5 volts and you'll get 10 volts there. 6 volts there, you get 12 there. If you have a 12 volt power supply. If you have an 8 volt power supply, you'll get 8 volts because it can give us 12 volts when you have 8 volts at our power supply. And that's how your distortion works. To have another very cool appliance of our non-inverting amplifier, we can force it to act as a comparator. Pretty much like in the previous episode I explained to how the Schmidt trigger works. This thing will compare voltages as well. Now imagine we have our voltages like this. Voltage 1 dashes, voltage 2 is like dots. Here is time. We apply our voltage 1 here, V2 there, and make our feedback network one resistor here and one resistor to the ground. Voltage output equals, if V2 would be 0, let's imagine it's 0 by now, then we'd get voltage 1 multiply 1 plus bracket R1 R2. If we had 1 volt here, we'd have 2 volts here if these guys were equal. But if we simply increase the resistance of R1 to infinity, we will get the infinity right there, which means we will get an infinite amplification. If you apply 0.0000005 volts right here, it would be positive relatively to this guy, which is 0 right now. So the difference between these two terminals would be 0.000005 volts, and it would be amplified endlessly. Well, mathematically, if you amplify this tiny number by an infinity, you'll get infinity. But we're living in a real world, so this guy will output our power supply voltage positive. It can't give us infinite volts, it can only give us 8 volts, which we're powering it with. If this guy is minus, say, 2 volts, then it is negative relatively to this terminal, which is 0 right now. We get minus 2, it gets amplified endlessly, and we get again minus supply voltage, minus 8 volts. So you see, we can compare if this is more than 0 or less than 0. Last question is, how do you get infinite resistance? Well, very simple. You just erase it. If there is nothing in here, it's like infinite resistance. Resistance blocks current to flow, and like if you have no wire, then current simply doesn't flow, right? Okay. Now we will make this R2 equal to 1 mega ohm. So if we do not apply any voltage here, it would go to ground. Then we can apply any kind of voltages right there. This voltage won't go to the ground too much because this resistance is quite big. Then you would have plus 8 volts here when V1 is more than V2, and minus 8 volts when V1 is less than V2. So let's look at this. Here is V1, it's more than V2, so say here is 8 volts, and it goes 8 volts the output until V2 becomes bigger than V1, then it drops to minus 8 volts and is there. So here we go, very handy, a thing that compares voltages and tells us if something is more or less than something else. Next up is a thing you already seen in the last episode about the oscillators. It's the CD4013 dual D-type flip-flop. It has outputs Q and Q inverted. It has the clock input, the data input, the set input, and reset input. It has some value in it. It's written into it on the rising edge of the clock. It looks at what it has at the data input and it writes it into itself. But if we asynchronously, at some random moment, put a logic 1 into set, it will force write 1 into itself. If we put logic 1 into reset, it will write 0. This is what we're going to use this time. Last time we grounded these two inputs and never used them because we needed this as a frequency divider. This time we ground the clock and data input. We will not use it. We will only use the set and reset inputs. Take the set input and send it to a banana jack. Take our reset input, send it to another banana jack, put some pull-down resistors of 10 kilo ohms. So if nothing is plugged in there, it references to ground. It doesn't take any kind of, radio shit flowing in air and suddenly turns 1 or 0. What we get here is a thing that on our command becomes 1 if we put our logical 1 from, say, our oscillator here, and 0 if we put our logical 1 here. Let's call this block a trigger. It has the set inputs, reset input, and out. So this whole thing is called a trigger. This is the output. Okay, moving next back to our operational amplifiers. Let's again remember the topology of our non-inverting op-amp. R1, R2, voltage in, voltage out, conjunction, conjunction. Voltage out equals voltage in, bracket 1 plus R1 divided by R2. Another good appliance of the non-inverting operational amplifier configuration is the voltage follower. Simply, it copies the voltage in and puts it into voltage out. Why would we need this? Because the operational amplifier almost draws no current, so simply current does not flow into this thing. And we can use this to buffer our voltages, so if we say need like 100 milliamps of power right there, but only have 5 here, we can put our source, which can only give 5 milliamps here. Its voltage will be copied right there, but it will be able to draw way more amps. So this thing gives us V out equals V in. But for this to be true, we need this guy to be 1. right? Because V in multiply 1 equals V out. And for this, we need this thing to be equal to 0. Remove our R2 resistor to ground. It becomes endless. We remove our resistor 1 and make it a short circuit, so it's almost 0. 0 divided by infinity gives us 0, which gives us 1 as the amplification coefficient, which gives us V out is simply equal to V in. Let's call this thing a buffer. It will be drawn like this. It has input and output. Now let's start building something that can actually help us with making sounds. First, we take our buffer. We put a resistor right here, 1 mega ohm, and the input here. So if we do not have anything here, it refers to 0 volts and gives 0 volts. What happens after this is it goes through a resistor, a capacitor to ground, and another buffer, and then to the output. So we have voltage input here, dashes, voltage out there, line. And say we have a square wave at voltage in. The buffer copies it from here to there, and then it starts charging the capacitor through the resistor. As you remember from the last episode, it takes some time, and this process goes exponentially. As this buffer draws no current, it simply copies the voltage from the capacitor and puts it into the output without messing with this block. So we get an exponential charge, an exponential discharge, exponential charge, exponential discharge. By altering the value of this resistor, by altering the R, the resistor value, we can get other slopes. This thing determines how much the square wave at the input is smoothed down. This thing is called a slew limiter. Let's name it the input, the output, slew limiter. We turn up the resistance. This capacitor starts charging slower and slower, thus making the charging slope longer and longer. The input is not necessarily a square wave, it can be anything you want to apply here, like some sequencer, even a wave if you have like a little capacitor right here, like 5 nanofarads or something. So it will simply determine how quick the voltage goes from high point to the lower point, or vice versa. One modification we can make to this thing is replacing the resistor with a network, diode right there, a diode right here. Put our potentiometer 1 here and our potentiometer 2 there. Connect them and put them into the capacitor. If we input our square wave, again, I'm looking at the square wave situation simply because it's very simple. It can be anything you want. So say here we dialed in 1 mega ohm. Here we dialed in 50 kilo ohms. So this resistance is kind of huge. So when the capacitor is charging, it's right here, when the square wave rises, it will be charging very slowly. But when it starts discharging back, when the square wave falls, we have 50 kilo ohms right there, so it does it way quicker, like this. Long charge, quick discharge. This way we can shape our waves. You can choose how quick it charges, how quick it discharges. So this is rise, this is fall time. So let's call it the rise-fall slew. It has input, output, and separate 2 controls for the rise rate and fall rate. Now we're going to combine our knowledge about this and make a fully functioning function. Okay, now that you know the basics, you're ready to go full analog. Which means we're going to do some fancy scary crap, specifically the vectors. Buffer right here, the resistor here, the capacitor, here, buffer here, and the output. In, out, resistor, capacitor, conjunction. We can make this a potentiometer, and like it can be even 1 mega ohm potentiometer. We can turn it with our hand, but it would be way more interesting if we could CV this thing. We're gonna go with a DIY solution because we're Synthcrap, and that means we make synthesizers out of crap, and we're gonna use a Vectrol. What is a Vectrol? Vectrol is a very simple and straightforward thing. We have our optoresistor right here. What it does, it changes the resistance depending on the light around it. So if there's a hell ton of light around it, its resistance is somewhere around 10 kilo ohms. If this resistor is put into a dark box, then its resistance is about something like 2 mega ohms. This resistor's model is GL55. And then we have an LED, light emitting diode, plus here, minus here, light here. And it changes its brightness depending on the voltage here between these plus and minus. So the trick is that we put these two guys into the light-proof enclosure, so no environmental light goes into, and the only light that appears here is the light from our LED. So literally what we get is a voltage controllable resistance. What we do right there is we simply remove this resistor and replace it with our photoresistor, and here we put our LED plus minus, put it into the light-proof enclosure, put this to ground, apply some voltage right there, and depending on this voltage, the resistance of this resistor, photoresistor, will decrease or increase, hence changing the voltage charge or discharge rate of this capacitor. Magic! Okay, now let's recall what blocks we have learned so far. We have learned our buffer. It has input, output, and it copies the voltage at the input to the output. We have our comparator, which has voltage 1, voltage 2, and the output. And it tells us if voltage 1 is more than voltage 2. We have our trigger, which has a set, a reset, and the output, and it gives us logical 1 if we tap set, and logical 0 if we tap reset. We have our slew limiter. It has input, it has output, it has one knob that determines how quick we charge and discharge, and we have our rise fall slew. It has two knobs, one for the attack and one for the release. Let's combine this into something I call the function generator. We begin with our trigger. The output of this thing goes into the rise fall slew. So we suddenly tapped set. It gave us 8 volts here, and this thing slowly starts charging, or quickly, as you determine it with the knob. The output of this thing goes to our output of the function and into two comparators. This comparator takes it as a plus input, and this one takes it as a minus input. So we have voltage reference ceiling and voltage reference floor, which are made by the voltage dividers from plus 8 volts to minus 8 volts. We get them out of here. And we have the outputs, seal, and the floor. Now, why would we need these outputs, and what the hell is this thing? Well, this thing can be either an envelope generator, an LFO, and like many more. Imagine we have sent a short impulse into our set. This thing outputs now 8 volts, logical 1. This rise fall slew is both set to very big resistances, both rise and fall. So it slowly starts charging, and the output goes like this. Then at some point it becomes more than voltage reference ceiling, which is somewhere about 7 volts. And this thing turns 1 from 0. We put our ceiling with a patch cable into our reset. And this thing resets our function. It gives us 0. It starts falling back to 0 and remains being there until we send our next impulse. So what we get here is an envelope generator. Imagine if we had some kind of a key or a button, so when we tap it here into the set, it starts going up and then automatically drops down. An attack release envelope, we can make it even better and patch the floor output into the set input. This comparator compares if our output of the function is lower than this voltage reference floor. So if this thing is lower than, say, 1 volt, this thing gives us 8 volts, logical 1. It goes back to the set and it sets the function to 1. The function starts rising. It rises until it crosses the voltage reference ceiling, which then resets the function and puts 0 into it. The function starts falling until it crosses the voltage reference floor, which then sets the trigger to 1 and it starts charging. Then it charges until it reaches the voltage reference ceiling, and voltage ceiling comparator resets the function and it starts falling back. We have an LFO. By trimming the attack and release or the rise and fall values on the rise fall slew, we can make it look like this, and something in between. Very interesting. Just as before, I started by sticking the faceplate layout print on my blank Texelite piece and marking the holes with an old drill bit. I put on safety gear before drilling it, cause safety first. First, I drill all marked holes with a 4mm drill. Then I enlarge needed holes to 6 and 8mm with a step drill bit. After painting and decorating the faceplate, I start mounting the parts on it. I start with banana jacks, red for outputs and black for inputs. Then I unpacked the switches and the LED holders and put them in place, but the LED holders somewhere were a tiny bit bigger than they usually are, so there was lots of rage, broken LED holders, and I won't show this to you. Then I made all the connections planned to be done on the faceplate. The LED grounds and output amount potentiometer grounds are all connected into one large bus, which later will be wired to the PCB. I also installed the output impedances and the LED resistors for comparator outputs. Had no place for that on the board. After getting all the parts for the build, I start by cutting out a clad board and preparing it for the photoresist and etching. Apply the photoresist. Expose to the ultraviolet light through the stencil. Put it into the etching liquid. Then drill all the holes for the parts and block the camera with my hair. And remove the photoresist with caustic soda. Look at how it goes off. I start assembling it with tracing all the airways on the PCB with a marker. I solder the board from less sticking out parts to the tallest ones, and the airways are simply pieces of uninsulated copper wire, so they go first. I use the remains of resistors and diodes After that, I put all the diodes and resistors in place and solder them in. They are the second least tall components on the board. Next are the IC sockets, then the trim resistors and ceramic capacitors, then the electrolytic capacitors and power bolts, and finally the potentiometers. After that, I screw my PCB into the faceplate and wire it up with the inputs, outputs, and the output potentiometers. Look at this neat wire mess. I check the Vectral LED, and as soon as it's working, I pack it into the solid black heat shrink tube. I end up with this cool module. Now let's check out this thing. Okay, so here we have our output, utility, and our two modules, the new one and the 6 oscillator core. Let's first hear what comes out of the oscillator core. It's simply a square wave, but this thing has a pitch control input, and we can put our function 2 output into this pitch CV input, raise the amount of the function, and then say patch this output of the oscillator into the rise input. Oops, too much volts. Okay, so clearly you can see that the pitch did rise. But when will it fall? Well, now we patch the fall output, now we patch the output of the comparator, which indicates when the function has reached its peak, into the fall input, and it automatically falls when it reaches its maximum position. But as soon as the rise overrides the fall, we can't make a pure triangle spike or something, so we change the mode to spike input, and let's see what happens. So yeah, you see? Now it's kind of a thing controlled by this oscillator, and if we do not provide the gate signal here, you see, it doesn't operate or anything, it just falls down. Then when it is triggered again, it will jump back. Let's write the frequency of the blue oscillator. Yeah, you see, it fell back on its own without the oscillator doing the thing. So yeah, why are these things happening? I know. Well, either way, we can take the... Now we can do the even more interesting thing. We can patch the floor comparator, which compares and looks if the peak has reached, if the function has reached its floor. We patch it into the rise input. Now it rises until it sees the rise, then it falls until it sees the fall, and we need to change the mode so it starts rising back. Now we can shape an LFO. Yeah, the second thing we have here is a comparator, so we can take the output of our function and provide it into the comparator, and then put it back into the pitch CV input of our oscillator. So it still does the LFO and the pitch thing, but now we can, well, maybe we should do like this, as to indicate something. Yeah, now we can set the threshold of it. And now we can use the comparator output to hard gate our oscillator. Hey, do you like gabber? I like gabber. We can change the threshold, and the time of the oscillator being active will change too. Yeah, now it's good. Now we can take our output and not run it directly into the mixer, but put it into the voltage controllable slew, which is right now in the audible mode with the small capacitors, like 5 nanofarads. And as the input of the voltage controllable slew, we provide our oscillator. And now the slew thing can do the filtering effect. Moreover, this effect is of course voltage controllable, because this is a VC slew, so we can put one oscillator into our clock mode, take its output, provide it into the fall, and then take the floor comparator of the first function and feed it into the rise of itself, so it will generate this kind of a dent. You see, it's even a little bit asymmetrical or something. Well, we will check right now. We will just take this function and run it into the CV of the slew. Rise the amount, offset it, so yeah, you see, kind of like VCF-like effect. But this thing can also process sequences and so on, of course. And this is not everything that this thing can do. You understand that the possibilities are way bigger than this. It's just like the demonstration of what the hell this model does. For more examples, you can look at the links below, because they are cool and were recorded with this kind of things. Yeah, very nice. Let's play around. Nice drone. Okay. Привет. Привет. плохо. Записываю вот.
So now we have a fully functioning function generator and a comparator and a slew limiter, which can also be a filter. Pretty neat! Thanks for watching my video! Also, big thanks to my patrons for supporting me. Without their help, I wouldn't have done anything because I wouldn't have money for doing anything. Please consider supporting me at patreon.com/analogtrash. I'll be very happy if you do, and I'll do even better videos. As for now, have fun generating functions. See you in the next episode.